Lecture, we're going to talk a little bit more about premixed flames and how those impact fire dynamics in general. Before going on as far as the formal lecture is concerned, I'd like to show a video that gives us some context to how fire behavior evolves and how some of the things that we're talking about now will connect to actual fire scenarios. So what we're going to do is we're going to take a look at this video that's produced by the National Institute of Standards and Technology, where they have or had a building and fire research lab that's been put into their general engineering group right now. But what we're looking at, and this is a relevant hazard, is a Christmas tree fire. And dry Christmas trees obviously pose significant hazard in terms of fires during the Christmas season, and some of the issues associated with it relate to larger issues in terms of fire safety in homes. So what you're looking at as far as this video is, you see it's a living room that's been outfitted with different types of sensors that we're not really seeing at this point. But one notable issue is you'll see this stuffed bunny rabbit in the foreground here, and that bunny rabbit is used as an indicator of a process called flashover, where the entire room becomes involved in fire. What we'll see is that the Christmas tree itself is ignited by an ignition process at the base here. I'm going to say this many times during the course of this course, that all ignition processes in some way originate as premixed flames. Premixed flames are the type of flame that were initially discussed. There's a transition to a non-premixed or diffusion flame. The entire Christmas tree is going to be engulfed in flame and fire. This fire can be thought of as a pump that lofts products of combustion to the highest parts of this compartment. So you can think about it as a pump of sorts, a blower. It's using the hot products sort of buoyantly are lofted into this upper layer, and they begin to stratify. So there's a process called a sealing jet that transfers these products of combustion across the ceiling, and once the ceiling is filled, it starts to bank down. These are very, very hot products of combustion, incomplete products of combustion that contain large quantities of carbonaceous material called soot. It's this soot that starts to radiate down on all parts of the compartment, and it'll be this soot that will ignite that rabbit. So let's just take a look at that. And so one of the issues from a fire safety perspective is people typically think that they have quite a bit of time to escape a fire once it's started. What you'll see here is that by a minute, this compartment is really untenable. It's untenable far before that, but you'll see that by a minute, it's really a problem, and you'll get transfer of the hot burnt products all over the compartment. So you see a fast ignition process at the base. I'm going to stop it. By 4 seconds, because of this kindling, this very dry Christmas tree, you have flame impingement on the ceiling of this room. The bright orange glow here is the broadband radiation from the soot particles, from the solid particles, and from the twigs and all this kindling. All this stuff is burning hot and is radiating brightly. We'll see that as we continue, that the products of combustion and the flames are spreading across the ceiling here. So by 11 seconds, you see that there's a significant impact on the visibility even within the compartment, and this stratification process that we've talked about, this layering, is already happening. So you see that there is a dark cloud of products of incomplete combustion that are banking down and are filling the compartment, or filling this room from the top. You see that this armchair has already ignited near the Christmas tree. we're intermittently seeing that lamp, and then all of a sudden we see that ignition of that lamp and lampshade. And by 32 seconds, we see that the rabbit itself is consumed and is ignited and is starting to burn very far from where the Christmas tree ignition process was. So we wanted to be able to describe a lot of those dynamics from first principles, or certainly understand and be able to characterize them. And that's, again, one of the issues that we're dealing with as we go through these lectures. All right, so in this specific lecture, we want to talk about types of flames, and specifically premixed flames, flame quenching, and flammability limits. As I mentioned earlier, all the fires that we're going to concern ourselves with will begin as premixed flames. Okay, and he said, well, what is a premixed flame? And so that's where we're going to go next. All right. So when we talk about combustion systems, typically from a sort of canonical and simple types of flames that we can anchor all sorts of other combustion processes on, we typically think about the fact that there are two types of flames. There are premixed flames, in which the fuel and the oxidizer are molecularly mixed prior to ignition and reaction. And there are non-premixed flames, where the flame is an interface between the fuel and the oxidant. So typically, the types of systems that have premixed flames are spark-ignited automobile engines, stationary gas turbine systems, the burner on your cooktop. So those are all premixed flames because we're mixing the oxidizer, the air, and the fuel prior to this reaction front. Non-premixed flames, a good example is a candle flame. Compression ignition engines typically burn in a non-premixed fashion. Interestingly, I said stationary gas turbines burn in a premixed fashion, but propulsion gas turbines, so what you might have in a jet engine, will burn in a non-premixed fashion. And so let's take a look at what I just said. Premixed flames, so let's summarize that. The fuel and oxidant prior to reaction. And we have an interface where we have fuel on one side and, for example, oxygen on the other side. Here we have an interface where we have fuel and oxygen on one side, and we have products of combustion on the other side. Okay, so uncontrolled fires eventually burn in a non-premix or a diffusion fashion. These non-premixed flames are also sometimes called diffusion flames. The idea being that it is a diffusive process, it's diffusive transfer processes that bring the oxidant and the fuel together. So this is diffusion controlled. Okay, so it's in fact the consequence of the mixing that changes the types of products that we get from premixed flames and non-premixed flames. So in premixed flames, the fact that the oxidant and the fuel are intimately mixed prior to reaction typically allows us to get near complete combustion. And so the products that we get are, for the most part, as certainly as we go towards stoichiometric combustion. And remember, stoichiometric combustion is where there is, on a global sense, an absence of fuel or oxidant on the product side. We are more likely to get water vapor and carbon dioxide for these premixed flame systems. For the non-premixed flame systems, because it's incompletely and improperly mixed, it's molecularly mixed at the reaction surface, we have all sorts of different products of incomplete combustion. And so in this diffusion flame, this fuel, so if we have this pure fuel coming in here, that fuel is hot in here, and it's breaking down, and it's producing soot, and it's producing all sorts of other different types of species. And so even by the time we get that to the oxygen, the types of things that are forming at the flame sheet are not allowed in some sense to go to completion. And so the products that we get from this are, excuse me, are typically incomplete products, carbon monoxide, soot, etc. Now, if we look at this Bunsen burner and we allow air to come in, as we've mentioned, there's this perhaps inner cone and outer cone, depending on the stoichiometry of the system. If this thing is globally rich, so we have more fuel than we have oxidant, so our equivalence ratio greater than 1, then we'll have a region here where we basically will burn out all of our oxygen, and then a later region over here where it's the excess fuel that burns perhaps as a diffusion flame. So we can have sort of this combination of premixed flames and diffusion flames depending on the amount of mixing that we allow in the system. Okay, so we're going to first discuss the premixed flame, and then we'll lead into what the implications are as far as non-premixed flames. So you might ask yourself, what exactly is a flame? And the answer depends on what application you're looking to design or what level of description you want. So at the simplest level, a flame is an interface. It's an interface between, in the case of a premixed flame, between the reactants and the product. So at that level of description, we can think about it as an infinitesimal interface where there's a temperature density jump. Interestingly, the pressure is essentially constant between the product side and the reactant side. So here we're saying again, it's dependent on the scale or detail that you're interested in, but in the simplest case, it's a discontinuity or an interface. And here I'm showing a flame propagating through a tube. And as you know, this system would have been ignited somewhere back here. The flame propagated away from that ignition process, and at this point is over there moving towards the unburnt gases. So the flame is consuming the reactants, which are the unburnt gases, and converting them to products. Now, I show some curvature here. So there are all sorts of factors that impact whether a flame is going to be curved or not. For a long time, people thought that the basic issue in terms of curvature was the boundary condition on the wall of this channel. So the assumption was that it's heat losses through the wall that might inhibit the propagation process at the wall relative to the propagation, for example, along the center line. So, commonly you have a cold wall of some sort. Okay. Let's get rid of that. So you have a cold wall, and that cold wall is causing something called flame quenching. And so that flame quenching is inhibiting the propagation rate of the flame, and so you can imagine that that would cause this relative slowdown in the flame propagation process, in the flame speed. But it's more complicated than that, and there are more likely stability questions and issues that drive it. The pressure distribution, and so I mentioned that it's essentially constant pressure in this system, but the minor changes in pressure and the motion of the front will distort the front from anything from so-called a mushroom shape, which is sort of like this, to a case which is actually the opposite of this, is a tulip shape. So you get things that sometimes look like this. And so this is a bit beyond what we need to talk about in this class, but again, I just want you to recognize that flames propagating in tubes have a sort of a variety of shapes, and depending on what the flame is propagating into, it'll take different shapes. The flame still, from sort of an idealization perspective, is just an interface. So a lot of times we'll talk about the abstraction of a flame as this one-dimensional, we'll call it adiabatic laminar flame. So this is a theoretical construct that allows us to infer and describe lots of different aspects of flame behavior. So again, we're just using that to understand what's going on in this system. So this one-dimensional adiabatic laminar flame moves at a velocity called the laminar flame speed, oftentimes given the symbol S sub u. Now, this laminar flame speed, this S sub u, is the speed of the front relative to the fluid ahead of it. So this is the speed at which the flame overtakes the unburned gases. So this, my right hand, is the front, my left hand is the unburnt gas. And so if the unburned gas is stationary, then the front moves at the laminar flame speed, simply overtaking the unburned gas ahead of it. If the unburned gas is moving, obviously the front is moving faster in a lab frame of reference to overtake the unburnt gas. Now, this laminar flame speed is a thermochemical property of the wave. So this thing is dependent on the composition, the unburned gas temperature, and the fuel. So this is what we mean by it's a function of the thermochemical property of the wave. Typically, its dependence on the temperature is as follows. So if we looked at SU-TP versus SU at a reference condition, we would oftentimes say that this looks like T over T0 to, say, the alpha power P over P0 to the beta power. So for a lot of hydrocarbon fuels that we might deal with, say alkanes, things like methane, propane, etc., alpha looks like about 2, and beta is sort of a weak negative function, so say minus 0.2. So it has a weak negative dependence on pressure, a very strong temperature dependence. So we increase the unburned gas temperature by a factor of 2, we get a factor of 4 increase in the laminar flame speed. Okay, so that's what we said here. Flame speed increases with temperature, decreases with pressure. post-flame temperatures are larger than pre-flame temperatures? Well, certainly, because what we're doing, remember that diagram we talked about when we were looking at the overall energy in a flame? So when we looked at the enthalpies in a flame relative to the temperature, we understood that what we're doing is that in the conversion process, in a flame, we're going from the enthalpy of the reactants to the enthalpy of the products. And because the reactants have a higher enthalpy at the same condition, that what we're doing is we're doing this conversion to temperature, that we're thermalizing, we're causing the energy in the bonds of the reactants to create higher temperature products. As we said also, the pressure change across a flame is essentially zero, and it's considered isobaric. Now, we'll talk about the mass conservation issues in a second. You know what, let me do that right now. I'm going to create another, I'm just going to create another slide here. Okay, let's see, how do we do that? So we're going to jump out of the let's keep that. And what we're going to do is we're going to insert a slide right there. Okay, so from a mass conservation perspective, we can figure out what the relative velocities are in the burnt gas and the unburnt gas. So one of the things that I want you to understand and be able to do is to think about a problem wherein we look at a closed tube. We'll again assume that this thing is well insulated. Well insulated means that it's adiabatic. The star is an ignition source, so we ignite at this location. We know that this thing initially is some flame kernel that grows and then becomes sort of this propagating wave, where we have our reactants on this side. Now, let's just play a game and think about what would have happened if we would have ignited this on the open end of a tube, again, well insulated, where, again, we get this process, we get this propagation process, okay? So, in both cases, we have some observed velocity of the flame. And what I'd like you to think about is which one is moving faster and why, okay? So, so the way we can treat this is, let's forget about the initial ignition process. So, we have this observed flame velocity. The assumption is that we have, in this case, again, just like in the bottom case, we have a burnt gas over here. We have an unburnt gas over here. So let's make sure I'm being honest here. VB is our burnt gas. These are our products. VU, unburnt gases. These are our reactants. And both of these are velocities, burnt velocity, unburnt velocity. Okay, now to be able to look at this from the perspective of mass conservation, we want to go to a frame of reference in which the flame is fixed. So a little bit of a tongue twister there. Fixed frame of reference for the flame. So to apply mass conservation, we're going to subtract off VF. So I have VB minus VF. V is now fixed, and I have VU minus VF. Okay? So I've subtracted off the velocities there. And I'm still going to play this game that, and you're going to say, that's kind of crazy. I'm going to subtract, I'm going to say, hey, look, you know, these are just flows, so I don't really care. I subtracted this off. I know the mass is conserved, so from my perspective, all I know now from a mass conservation perspective is that the density over here times the velocity of the stuff here had better be equal to the density on the right-hand side times the velocity on the right-hand side, okay? And so ideal gas equation of state with an approximation. So fire is complicated, so we can make sort of interesting approximations like this. Let's say that RU is equal to RB, so the gas constants are the same. So we know it's isobaric, so PU, ρU, RU, TU is equal to PB, ρB, RB, TB. Okay, so this is our isobaric constant pressure approximation. RB is equal to RU, so this says that ρU over ρB is equal to TB over TU. So remember we said that when we're talking about the temperatures in flames, we said typically TB might be something like, we'll go with 2400, and TU says 300. So ρU looks like 8 times ρB. Okay, so the unburnt gas density is about 8 times the burnt gas density, or the burnt gas density is 1/8 of the unburnt gas density. Now, what we're trying to do, for example, is we're trying to identify here so the thing we might be asking here is, what is that VF? What is that observed flame velocity? If we, for example, know what the mixture is. We had to have known the mixture a little bit to know that TB is 2400 and TU is 300 K. So, you know, we throw out a case that it's methane. So we say, okay, let's say we had been working with methane here such that this is true, and, you know, for a stoichiometric mixture. If it's methane, I happen to know, and we can look in tables, that the laminar flame speed, which is VF, so the definition of laminar flame speed is VF minus VU, is about, and, you know, we'll look at the exact number, but it's about 50 centimeters per second, or half a meter per second. Okay, so we're getting there. So we know that VF minus VU is SU, so we see that this is actually minus SU over here. So we multiply by, well, let me do one last thing, okay? So the question might be, well, this is getting interesting. I'm going to rewrite it. We say ρB VB minus VF is equal to minus ρU SU, okay? So remember, I'm doing the minus. I'm putting a minus sign there because I have VU minus VF, and really VF minus VU is the definition of the laminar flame speed, which is 0.5. So I'm in a situation where I have this. Okay, now the question might be, okay, well, what is VB here? What's this VB? Well, let's think about this from a thought experiment again. So from a thought experiment, if this is a closed wall, okay, it's a closed wall, if I make a measurement of the velocity right next to that wall, what do I expect the velocity to be? I expect the velocity to be the velocity of the wall. Well, the velocity of the wall here is 0 meters per second. The wall isn't moving. And so as I do that, and as I think about what the velocities, what might change the velocity, well, the things that would change the velocity would be changes in the density. So there's a statement of conservation of mass that says this. It says that d rho dt plus d rho u dx. So this is a differential form of conservation of mass is equal to 0. All right, and I don't expect you to know this, but I just want to make sure that you're happy with where I'm going next. This says rho u, if I integrate this, is equal to minus the integral of d rho dt dx, okay? So as I look at the mass flux anywhere, once I know it's somewhere, and where I know it to be something is at the wall, where it's 0, it's equal to minus d rho dt dx. Well, as I look at any of these locations, I'm assuming that this is a constant pressure, which is a reasonable approximation here, and the density is not changing with time. So if the density isn't changing with time, rho u is always going to be equal to whatever rho u was at the wall, which is 0, okay? So what we see is that VB is equal to 0. So this is great. It says that minus rho B VF is equal to minus rho U SU, or VF is equal to rho U over rho B SU, which is equal to, we see it's equal to 8 times 0.5 meters per second. So we get 4 meters per second. So even though the fundamental velocity is 50 centimeters per second, half a meter per second relative to the unburnt gases, because the unburnt gases are moving because of this expansion process, the flame has to overtake them, and it has to go much faster. So sometimes we call this an expansion velocity. So it's the velocity associated with this density change that causes this expansion and then requires this overtake of the unburnt gases. Okay, does that make sense? And what I want you to think about is what happens in a situation like this, where, so this was, we did all of this for the problem where we ignited on the closed end. I want you to be able to tell me what VU is going to be for the closed end ignition problem. And then for the open end ignition problem, I want you to tell me what VB, VF, and VU should be for the same problem where SU is 0.5 meter per second, okay? So think about that problem. You need to be able to analyze a problem like that. And it's just the same processes we're doing here. I'll give you a hint. Here, VU is equal to 0, okay? Because it can't go anywhere. So the expansion is all going in this direction, and you should be able to figure out what's going on there, okay? So this is not a hard problem, and look at that. Now, what we did is we looked at one level of approximation for the flame, this interface approximation. But, you know, there's a lot more depth and importance to what happens within the flame. And so what I'm going to tell you, so now as we look at this slide, is, okay, up until now we said that the flame was an interface. It was a jump. We said it was a jump in the temperature, so we sort of made this approximation that the temperature was 300 K at the flame. It jumped to, say, 2400 K. So we had 2400 K over here, 300 K over here, and in some sense, we said that, okay, the reactants, so our fuel and our oxygen, they had a concentration that was high prior to the flame. They jump down, and then they're 0 after. The products do the exact opposite. Fantastic, except for the fact that that's an oversimplistic perspective. And so what we want to say is, well, what are the details of what actually happens in the flame? And how thick is this region that we had been saying is an interface? So we'll start off with this as far as the thickness. The flame thickness is on the order of hundreds of micrometers. So we're going to go with, say, 100 micrometers here. And we'll do this from something called scaling analysis. So the flame thickness is that sort of order of magnitude. We're going to find out that the processes that control this thickness are dominated by diffusional transfer processes. So this is going to be really it's going to be, actually it's a little bit more complex. It's a convection diffusion balance for the most part. So we're going to see that's the thing that perhaps describes that. And even within that 100 micrometers, so remember 100 micrometers is about the thickness of a human hair. That even within this 100 micrometers, there is an incredible amount of complexity and all sorts of things that are happening, among which the reactions take place. So within that 100 micrometers, there's a region probably about 10 micrometers where the actual reactions take place, where the conversion processes are happening, where the detailed evolution of all the different species that you probably can imagine that might be formed from CHO and N are forming, are breaking apart, are living or dying. There are intermediate species that we don't see on the product side and we never saw on the reactant side that are born and die in that small zone. So part of the complexity in fundamental combustion science is identifying the appropriate kinetic mechanisms, the reaction rates, the reaction rules and laws that govern how this system behaves. Now, if it were just as simple as trying to describe the laminar flame speed, we can almost do that from curve fits, and there are sort of theoretical constructs that allow us to do that from basic curve fits. If we wanted to do it from fundamental principles, from atomistic descriptions, it's unbelievably challenging and complex. So again, there's a hierarchy of how we might be able to view this and the level of detail required to answer any particular question. One of the things I think is important and fascinating is that when we're dealing with fire, so think about a fire, think about a garment, you know, a sweater burning. The products that come off the sweater are not simple alkanes or alkenes. These are very complicated chemical species that come off of the burning of any true condensed phase fuel. As a science and as a discipline, combustion and fire are not really at the level to describe that in a meaningful way, which is a bit troubling. Nevertheless, approximations are made for us to move forward in terms of being able to describe the impact of the burning of these things. Now, you would have an incomplete knowledge of fire and combustion if you aren't aware of the fact, though, that even though that we may describe things in global terms and using approximations and correlations, it's, again, useful to understand the underlying issue. And that's why we're talking about this detail of a premixed flame. So people spend their careers describing the evolution of these species inside here. If one were doing this computationally, one would have to solve many, many tens, hundreds of partial differential equations to identify the evolution of these species. So the way we would do it computationally is we would obviously write down the most important conservation principle, which is mass conservation. We would write energy conservation. We would write species conservation. So this is how each of these individual species, which I might denote by Y sub I, which would be the mass fraction of species I, how these guys evolve. And depending on the geometry and the flow, I would likely need momentum conservation, tell me UVW, what the flow profile looks like, so where things are being distributed, where this interface is going, etc. And so depending on, and of course, from a closure perspective, I need an equation of state. So these are the types of things that would have to be looked at, solved. This is one differential equation. Energy conservation is at least one, and if we couple it with radiation, then we have to solve the radiative transfer equation. Depending on the number of species that we're tracking, we could be tracking 200, 300, again, 1,000 species. Momentum, we're solving for UVW in a three-dimensional case, and then we have a constraint of this equation of state. So, these are typical profiles that occur in this system. And again, there's nothing particularly difficult about sort of the simplest level of trying to generate these profiles. As I said, here are the types of conservation equations that one might require. In just a one-dimensional flame problem, so remember that was that flat profile. That's not particularly flat. So again, if we're looking at this tube and we're interested in this flame propagating in the tube, we're solving mass conservation, where this is the DDT terms are all our transient terms. Is the divergence of the mass flux. So in sort of a vector notation, you perhaps write it as that. And of course, that can be decomposed. And we used that earlier. In terms of the species conservation, again, our transient term, I'm going to label that T. This is our convective term. So sometimes we say either convective or advective term. So this is the transport by bulk flow of the species I. So this is for species I. This term is our diffusive mass flux, sometimes called J sub I. So there's a diffusion process, and we've modeled J sub I here using something called Fick's law that you probably know from other applications. And in its sort of in its base form, what we're really doing is we're convecting rho yi with a diffusion velocity. But this Fick's law approximation lets us model it as a gradient diffusion process. And this is our source or sink term, our chemical source or sink term, which is typically in an Arrhenius form. It's a function of typically like a yi, yj, and temperature. Energy, transient, convection. This is our pressure transient source term. So this would give you like the isentropic relations if you just had this term and say the dt dt. This is our thermal diffusion term, which we understand to be just a conduction term, but it's the same physics as so this is still a diffusion type process. It's a diffusive flux. And this is, of course, Fourier's law. So Fourier's law and Fick's law are analogous physical processes. And this is our reactive source term. And momentum conservation, of course, there's a momentum diffusion term that's mediated by our viscosity. And the other terms are very similar to what we described. Okay, so from a scaling perspective, so first of all, what does scaling mean? Scaling is a process by which we use algebraic relationship I'm going to change that. It's a process in which we use algebraic, maybe manipulations is a better word here, manipulations of underlying equations to determine global solution properties. You say, what the heck are you talking about there? Okay, so in normal words in English, we have these differential equations that we just showed and discussed that govern how a flame evolves. We believe these to be true. The reason we believe these to be true is because we are not working in theoretical physics. The formalism, the laws that we use are very well established, have been tested. So we don't have to create new laws. All we have to do is understand the interrelationship of the parameters within the laws that we're using. Now, the formal way to do this, the complete way to do this, is to solve those differential equations. And, but they're nasty. They're nonlinear, they're coupled, there's many of them. And so it's, for any given scenario, it takes a lot to do that. But if we are to look at those relationships, we can identify how the parameters have to interact in them to be able to come up with some overall and general relationships and results. And that's what scaling is. So if we, for example, say we'd like to understand how thick the flame sheet is or how fast the laminar flame speed is, we might say to ourselves, well, let's look at the energy equation. So we'll look at, say, energy conservation. And if energy conservation were written for a 1D steady system, it would look like this. We would say rho u c sub p dt dx is equal to, and d dx k dt dx, and I'm just going to put plus q dot triple prime, okay? So we'd have a convection term, our diffusion term, which again is just a conduction term, and our heat release rate, our source. Now, I'm going to say this. I said, okay, well, look, we want to identify either the laminar flame speed or the flame thickness. And so the one thing about scaling is that it requires a little bit of insight and knowledge, a little bit of intuition about the physics of the problem. In passing, I said that this term, the source, occupies a very small portion of what you might think of as the extent, the region over which the variations in the flame occur. Okay, so let's think about that. the places where reactions occur are very thin compared to the overall extent of where the flame has its thickness. So to first order, we can neglect that aspect of it. And so one of the things that allows a lot of flame theory, premixed flame theory, to take place is to recognize that the premixed flame is a convective diffusive balance, okay? And I know that some of this is not intuitive, and so I'm trying to walk you through it. Now, if we integrate this term, this rho u Cp dt dx, so we're doing this in a constant property sense. So we integrate this, we get rho su Cp Ti minus Ti. We've inferred, we've assumed that the velocity that we looked at above can be represented by the laminar flame speed. When we integrate the diffusion term, we say, hey, the length scale over which we're going to do this is going to be delta R. And so this is a reactive, as a flame front thickness, and it's really this preheat thickness. I don't know why I put R here, but it's a preheat thickness. I'm going to change it here. So if that's the case, just algebraically, I can modify it like this. I can tell you that SU looks like K over rho C sub P times all this stuff, okay? And, you know, frankly, I like to think about it slightly differently. I like to think about this problem where I say, I know delta, I want to figure out, I know SU, I want to figure out what delta is. So to just invert this, I would have the delta, because this is 1 over delta, I'd put delta over here, looks like alpha over S sub U, and this factor is basically 1. This T burned minus T ignition over T ignition minus TU. I don't like this term. I just like to think about this as 1. So I like to think about, to first order, delta looks like alpha over SU. Alpha is the thermal diffusivity, and of course SU is our laminar flame speed. So let's just, for fun, play around with some numbers here. So this isn't going to be right because we're doing it in constant properties, but let's just go through it. So thermal diffusivity at cold conditions, so for air, is 20 times 10 to the minus 6 meters squared per second. The laminar flame speed, as we said before, is about 1/2 meters per second, right? Because we said it was about 0.557 centimeters per second. So we have, what do we have here? We have 40 times 10 to the minus 6 meter. So we're approximating, excuse me, approximating it as 40 micrometers. Remember, earlier on I said it's about 100 micrometers. Now, the thermal diffusivity, we'd have to correct the thermal diffusivity for actual higher temperatures. So that would clearly boost it. And in fact, you know, if we boosted it to some average value, this would probably be more like 250 or 300 micrometers, because the thermal diffusivity, the way it depends on temperatures, to the 1.7 power. And so you can see that if we're using, say, 1,000 degrees or something like that, then we have a considerably larger value for delta. But at least you see from a scaling perspective what the issues are. Okay, so we already talked about the fact that the flame speed increases with temperature and decreases with pressure. And this is a case for methane. So what I'm showing here is the temperature at 291 K, 1 atmosphere. When we go to half an atmosphere, we get a reduction in the propagation speed. As we go to high temperature, of course, we get a significant increase in the laminar flame propagation velocity. What this shows is that there are greater hazards at high temperatures, high reactant temperatures than at low reactant temperatures. Okay, this gives you some correlations for the laminar flame speed in terms of, so these are, I believe, from a paper Keck and Met-Gauchi. It's a relatively old paper. I would say 1981. But the values are fixed, and you can find this in most combustion textbooks. So here's our negative pressure coefficient. Here's our, again, temperature coefficient, gamma. We can correct for both of these with the equivalence ratio. Remember, the equivalence ratio is fuel over air divided by fuel over air stoichiometric. And our base, so these are our reference condition laminar flame speeds. Up until now, remember, I've been saying that it's about 0.5 for methane. It's more like 0.4, but just for me to do some of these calculations, I'd like to use 0.5 because it's 1/2 and I can multiply it. But you see, hydrogen, my goodness. Remember, we were saying that, with the expansion velocity for methane, where we multiplied it by a factor of 8, we would get for this 320 centimeters per second. Well, gee, hydrogen is already at 210, and so you see that when you put a factor of 8 on 2 meters per second, you have a very significant expansion velocity. And acetylene is another one where, it's very dangerous because it's just a very fast flame speed. So, to conclude, laminar flame speed, a lot of effort has gone into experimentally and analytically figuring out what it is. The analytical idea is it just gives us obvious behavior and gives us trends and understanding of what the issues are. There are a whole range of numerical tools and codes that are used to predict laminar flame properties. The most common in the combustion community are these Sandia laboratory codes, Premixed, Chemkin, Tranfit. Actually, they're managed now by a company called Reaction Engineering. So it used to be called the Chemkin package. And if you search online, that's how you might find it still. Okay, so that concludes our discussion about laminar flame speeds, and we will continue in the next lecture to talk about ignition processes and again, just step through some of these issues.